Hi, in this video I will talk about some differential equations and how they are useful in understanding real-world situations. These differential equations describe changes over microscopic amounts of time and microscopic distances, but they can also help with predicting behavior at very different times and positions. In other words, the differential equations help bridge the gap between microscopic changes and macroscopic changes. In this video, I'll only consider one-dimensional situations. However, the analysis is very similar when 3 dimensions are considered. Also, in this video, I will use subscripts to indicate derivatives. Here is Newton's second law. The second time derivative of the position of an object is equal to the net force acting on the object divided by the object's mass m. As an example of how Newton's second law can be used, here is an approximation of the equation which describes the motion of a pendulum when no friction forces are present. The second time derivative of the position x is determined by the gravity acceleration constant g, the pendulum length L, and the current position x. A good way to use an equation like this is to find an equation which describes the position x, which is compatible with the differential equation, but which does not include differential terms. One such oscillation equation is here, where a is the amplitude, f is the frequency of the oscillation, t is time, and phi is an offset phase constant. By substituting this motion equation into the differential equation, we can solve for the frequency value. Notice that the frequency is a macroscopic value, but we calculated it using a differential equation which describes changes during microscopic amounts of time. If we have additional information about the x value at particular times, we can then determine the a and phi values, which would make it possible for us to make predictions about the x values at many different times in the far past or the far future. Here is an approximation of the key equation which describes sound waves. It can be derived by considering the motion of atoms in a very small amount of sound-carrying material. It says that the second time derivative of the pressure P is dependent on the bulk modulus K, the density ρ, and the second position derivative of the pressure. For background, the bulk modulus K is a measure of how much the density of a material changes when it is compressed. I will now combine this equation with a pressure equation which is consistent with it, but which does not include differential terms. Here is a wave equation which fits. Here, K is a value related to the wavelength called the wave number, and V is the velocity of the wave. By substituting this wave equation into the differential equation, we can solve for the velocity. Once again, we have determined a macroscopic value of the velocity using the microscopic information in the differential equation about how pressure changes during tiny increments of time. Another interesting situation is when a string is pulled tight and vibrating, which is how a guitar produces sound. This vibration can be described with this differential equation, which can be derived using Newton's second law applied to a very small section of the string. Here, y is the deviation of a small part of the string from equilibrium, m is the mass of the string, l is the length of the string, and F is the force pulling on the string, which is also called the tension. The fact that the ends of the string are fixed limits the types of motion equations that are consistent with the above differential equation. Some of these equations are described at the bottom of the page. Here lambda is the wavelength of the sine wave describing the string deviations. Here are diagrams showing how the fact that the endpoints are fixed limits the type of wave patterns that have strong oscillations. Substituting this motion equation into the differential equation produces a set of frequency values which are described using the set of positive integers. After a string has been pulled and released, strong and persistent string vibrations will only be present at these frequencies. Notice that the frequency values are evenly spaced. As a demonstration, here is a spectrogram produced by a guitar string after it is pulled and released several times. The horizontal axis indicates time, the vertical axis indicates frequency going from 0 Hz to 3000 Hz, and the color indicates the intensity of sound. Notice that strong persistent sound is only produced for certain frequencies, and that those frequencies are evenly spaced. So far, I have discussed these differential equations. In each case, an equation consistent with the differential equation was substituted into it, and a quantitative result was produced. There are many other important differential equations that can be used in similar ways. They include equations for light waves and for particle waves described by the Schrödinger equation. Thanks for watching.